Hi students. So under the subject algebra number theory, we are into unit 2 finite fields and polynomials. This is my second lecture. The topic for today will be roots of polynomials. So let's start. So before getting on to the definition of root of a polynomial, I want all of you to just recap over what is a polynomial is, right? In my previous lecture, I had explained what is a polynomial. So polynomial is some algebraic expression in one variable, right? So we can say x cube plus 3 is in a polynomial, x plus 2 is also a polynomial, etc. So what are the operations identified over there? Addition, subtraction and multiplication. Okay. Now what is not a polynomial? So whenever a variable carries negative powers and a variable carrying square root powers, that is whenever square root is present in the power or a negative power present in the power of the particular variable, then that will not be considered as a polynomial, right? So now you already know what is a constant polynomial, what is a zero polynomial, etc. So now let's see what is the root of a polynomial. So let R be a ring. I guess everybody remembers what is a ring. Ring is a set with two binary operations with identity 1, and let f of x is equal to a naught plus a1x plus a2x square plus so on plus an x bar n belongs to R of x. So here I see it's R of x and here it is mentioned as R. So now few might have a doubt. What is the difference between R and what is R of x? R is a ring, whereas R of x is a collection of polynomial rings. So try to understand the concept. So this will be a collection of all the polynomial rings. Now they are taking a polynomial. What is the degree of this polynomial? The highest power. The highest power of the polynomial is n. So now with the degree, f of x is greater than or equal to 1, they are saying. So necessarily we are going to take a particular polynomial mentioning its degree is greater than or equal to 1. So always take a polynomial greater than or equal to 1. Why so? Why they are mentioning it as greater than or equal to 1? Why can't it be equal? Why can't it be less than 1? Right? Why can't it be 0? There is another option. We cannot be negative. So why can't it be 0? So if I'm going to make a degree of a polynomial as 0, so what do I actually mean? I mean the power of that particular variable is 0. So if I write x to the power of 0, so later case I will arrive only at the constant. I don't have the variable. So to find a root of the polynomial, I need to have the variable inside. So for that, minimum one variable at least should be there. At least minimum x or more than that. That is why they are mentioning it as greater than or equal to 0. Unless and until there is no x, where will I go and substitute the value of x to find the root? So that arises as a question. So that's why the degree of f of x is greater than or equal to 0 is specified. Now we move on to the definition of root of a polynomial. An element A which belongs to R. So from R I'm going to take an element A that I'm going to declare as a root of that particular polynomial f of x if I substitute that a inside the polynomial, I'll be getting a naught plus a1 into a plus a square into a square plus so on an to the power an, which is equal to 0. So actually what does it mean? If I substitute f of a, which means if I declare any variable that is a root, or sorry, any element in R, if I'm going to say it's a root, it should satisfy that particular equation. This you would already studied in your lower classes. So saying that how will I get the roots? For a quadratic equation, I start equating to 0. I factorize it. I get the roots. Right. Same thing you can do. For a square equation or a cubic equation, you can go ahead. Right. But whereas for higher powers of a polynomial, it is going to be difficult for us. Right. Okay. So now let's continue. So now we'll have a theorem for it. So the theorem says that if f of x belongs to capital F of x, right, as degree n greater than or equal to 1, then prove that f of x has at most n roots in capital F. Right. What is capital F? Capital F is a field. So what is at most means? It is maximum. Okay. So whenever you consider an equation, a polynomial with a degree greater than or equal to 1, then you say there are at most maximum only n roots will be available. So how are we going to prove this theorem? I guess we prove this theorem by mathematical induction. I hope everybody remembers what is mathematical induction is. You already studied this under discrete mathematics, right? So mathematical induction on the degree f of x. So how do I use mathematical induction? There are 3 steps. First, number 1, so we say we prove for n is equal to 1. Number 2, we assume n equal to k is true. And for the third one, n is equal to k plus 1 is to be proved. So 3 steps are there in your mathematical induction. So the same thing applications I'm applying here for this particular theorem. If f of x is degree 1, then f of x is equal to ax plus b. So you may wonder how this ax plus b came. It's just a normal representation of the polynomial. You already remember your polynomial starts with a naught plus a1x, etc. So which means a naught is replaced by b here and a1 is replaced by x for the convenience sake. Right. So now f of x is equal to x plus b, where a and b belongs to capital F, and a should not be necessarily not equal to 0. Here it's a very important condition, because if a is equal to 0, what will happen to this particular polynomial? This entire term, there won't be any x existing. Okay, with f of minus of a power minus 1, b is equal to 0. This is the function what I'm defining. F of x has at least one root in f. Okay, so if degree f of x is as 1, so what does it mean? It has at least one root in f. Right. Now what I'm doing is, if c1 and c2, I'm going to take two numbers or two elements, c1 and c2 are both roots. Then, so when I say they are root, what should happen? When I substitute f of c1, you should get 0. When I substitute f of c2, your answer should also be 0. That's why they are writing in this condition. AC1 plus B is equal to 0 is equal to AC2 plus B, which is equal to f of C2. Now, this you have already studied. Cancellation law in a ring. By cancellation law in a ring, AC1 plus B is equal to AC2 plus B, which implies, so you have two types of cancellation laws, right cancellation and left cancellation laws. So here you will be getting B and B will get cancelled. So AC1 is equal to AC2. Since f is a field and a is not equal to 0, so what happens? Again, you apply the cancellation law. So AC1 is equal to AC2, which implies C1 is equal to C2. So f of x has only one root in capital F. Right? So which means C1 and C2 both are the same. So I can say there is only one root here. So for 1 it is proved. Now assume the result is true for all the polynomials of the degree k greater than or equal to 1 in f of x, because it's mathematical induction process. So third step will be considering a polynomial f of x of degree k plus 1. If f of x has no roots in f, the theorem follows. Otherwise, let r belongs to capital F, f of r is equal to 0. By factor theorem, okay, factor theorem is just dividing a polynomial by another polynomial. Okay, so this is the divisor. Okay, now we are going to divide one polynomial by the other polynomial into the quotient, where g of x is degree k. Consequently, by the induction process, g of x is at most k roots in f, and f of x is at most k plus 1 roots in capital F. Okay. So let's move on to the problem section now. So the first problem is finding the roots of a polynomial x square minus 2 over the real number capital R. So it is just observe, it is just a what type of equation it is? It is a quadratic equation. So it's just they haven't mentioned anything more complicated. They've just asked you to find the roots over the real number R, right? So since it's a quadratic equation, you can easily solve it. So given the polynomial x square minus 2 over R, you are equating that x square minus 2 is equal to 0. which implies from here you can say x square is equal to 2. So from here, what is the value of x? X is equal to plus or minus root 2. Now after getting the roots, right, you have to check whether these roots are lying inside R. What is R? It is a real number. So root 2 and minus 2 definitely belongs in R. So therefore I declare that minus root 2 and plus root 2 are the roots in R. Right. So the extension of this problem, suppose if the problem is asked over Q, here it is asked over R, and here suppose if they are going to ask you over Q, then okay, what is the roots again? There won't be any change in the roots, but I have to check whether these roots lie or belong to Q. What is Q? Q is rational numbers. So I already told you this belongs to real. So this will not belong to Q. So therefore, under Q or over Q, there are no roots from this polynomial. Is that clear? So depending upon what it is specified, whether it is R or Z or Q, you got to discuss this. Okay. Suppose if this is discussed over C, complex numbers. Is this a complex number? It is not a complex number because there is no I over there. So definitely it does not belong to C. That is what my conclusion will be. Okay. So we move on to the next problem. So problem number 2. Problem number 2 says determine all the roots of f of x is equal to x square plus 3x plus 2 which belongs to z6 of x. Now this is a special case where they are mentioning the modulo of 6. Right. So now you can ask me, why can't we do the same procedure as we did in the previous problem since even here we have a quadratic equation. So can we substitute this quadratic equation? Where can we solve this quadratic equation and get the values and check? No, we should not do that here. Why? Because they haven't told us whether it's over R or whether it's over Z or C or whatever it is. Here they have clearly mentioned it as the modulo of 6. So I'll tell you how to find the modulus of 6. Right. So step by step process. Please pay attention. It's a very important problem. So what do I do? F of x is equal to x square plus 3x plus 2. Right. So first I'm going to take the polynomial. What is given I'm going to write. Now I'm going to write what is z6. What is z6? Z6 will be containing 6 elements. So try to understand this concept. When I write 6 here, I should have 6 elements in that particular set. If I have 10 here, I should have 10 elements here in this set. But the elements of the set should start from 0. So 0 means 0, 1, 2, 3, 4 and 5. I will stop at 5. Because if I include 6 over here, the number of elements in the set will exceed 6. So since I am starting it from 0, I will stop at 5. So this can be same for all those modulo declaration. Suppose if I write Z10, I'll be starting from 0. Where should I end up? I'll be ending up at 9. Okay. Now we shall verify and find the roots. So how are we going to find the roots? So what we do here, we have 6 elements, right? So take element by element, one by one and substitute in this f of x. So first I take 0, substitute here. If I substitute here, what will I get? 0, 0 and 2. So I'm writing it 2. Okay. Next take 1. Substitute 1. 1 plus 3 plus 2. So what's my answer? It's 6. So I'm writing 6 here. I'll come to the modular division later. Now coming to 2. If I substitute 2, it's going to be 4 plus 6 plus 2, which is 12. Coming to 4, I'll be getting 4 square. 4 square is 16 plus 12 plus 2. So it's going to be 30. And the last one, 5. If I substitute 5, it's going to be 25 plus 15 plus 2. So it becomes 42. Is that clear? So first, whenever a modulo thing is mentioned, you write down all the elements and start substituting one by one in your function f of x, and first you tabulate it. Now comes the discussion under modulo. Now what do I do? First, since modulo is given, I go and find out whether what is the answer I'm getting here. So if I see the answer here, the answer I got it is 2. 2 is less than the modulo 6. Is that clear? So it's a less than number. It's a smaller number than 6. So I cannot divide or cannot do anything with that, say, with that 2. So I'll write the answer is not equal to 0 because 2 is not equal to 0. Is that clear? Right. Now coming to the second one. What is the answer I got? The answer I got was 6. So 6 is equivalent to that 6, right? When I divide 6 upon 6, I can divide 6 upon 6. If I'm going to divide 6 upon 6, what is my remainder? Remainder is 0. So this is a congruent symbol where I write 3 lines. Okay. So what I should write the remainder in under what modulo I have done it. For 12, 12 is divisible by 6. So what is the remainder? 0 again, mod 6. Now coming to 20. If I take 20, if I'm going to divide this by 6, how many times? 3 times. 6 3s are 18. Right? So what is the remainder? My remainder is 2. So now coming to 30. 30 is clearly visible by 6. So if I'm going to divide 30 upon 6, I'll be getting 0 remainder. I'm writing only the reminders. Make a note of it. It's not the quotient. Now coming here, 42. If I'm going to divide 42 over 6, it's perfectly dividing because 6 8s are 48, 42 and the remainder is 0. So I'm tabulating the 0. So here, after, see, first step is I had written all the elements in Z6. Second step is I have started substituting all the elements in Z6 in my f of x and noted the values. Third step, I have applied the mod function and I found out the remainder here. And now I'm going to give my declaration or my conclusion. So what will be my conclusion will be? So 0 is not a root. Why 0 is not a root? Since I substitute 0, I'm not getting a answer as 0. Only if I substitute one value and the answer is 0, then only I can declare it as a root. So my answer is not 0, right? So 0 is not a root. Now, since I substitute 1, what is my answer here? 0. So 1 is a root. 2 I substituted, my answer is 0 here. Look at the remainder. So therefore 2 is a root. 3 I substituted, the remainder is 2. So it is not a root. 4 I substituted, the remainder is 0. So 4 is the root. 5 I substituted, 5, the remainder is 0. So 5 is the root. So you just finally conclude, therefore the roots of f of x are 1, 2, 4 and 5 under the modular division of Z6. Is that clear? So third problem, same type of problem. Find all the roots of f of x is equal to x square plus 4x in Z12. So in Z12, what will I write? 0, 1, 2, 3, 4 up to 11. So what do? I start substituting 1 by 1. So first I substituted 0 here. If I substitute 0, the entire answer will be 0. So automatically I can say when my answer is 0, I can say that particular element is a root. Second, substitute 1. If I substitute 1, the answer is 5. 5 is definitely less than 12. So I can't divide 5 upon 12. So it is not equal to 0. Therefore 1 is not a root. Substitute 2. 2 if I substitute is going to be 2 square is 4. 4 into 2 is 8. So 4 plus 8 is equal to 12. 12 can be divided by 12. It's just perfectly dividing and my remainder is 0. So since my remainder is 0, I can call this 2 as a root. Same way for 3. 3 if I'm going to substitute is going to be 9 plus 12. So my answer is 21. And if I'm going to divide 12, okay, 21 by 12, my answer remainder will be 9, which is not equal to 0. Therefore 3 is not a root. Clear? Likewise, you start substituting for 4. 4, the answer is 45. For 12, the remainder is 9. Not equal to 0. So 4 is not a root. Similar way, f of 6. Okay. Likewise, you just keep dividing, substituting each number and get the value and divide it by 12. Okay. So divided by 12. How many times over here? So dividing and you're getting it a remainder as 5. 96 is perfectly dividing by 6. 117 will not be divisible by will not be divisible by 12. Likewise, for each number you start dividing and finding out the remainder. The very simple fact is, when you get the remainder as 0, you call that particular element as a root. If not, you call it is not a root. So finally, jot down all the elements which are the roots of f of x over z12. Thank you so much. Hope you understood the roots of polynomials.